Hi, this is David Green from IA Incorporated. I'm going to run through some FSK range processing. This is an example I have in MATLAB. And what we start out doing is I set up my starting variables. We have the speed of light, the carrier frequency for the radar, the frequency shift in the FSK. This is the step between the two frequencies that are sent out. And this is my, my chirp length, or basically how long the sweeps are. I then go ahead and select the file name that I want to process. These are all recordings that I've done with the Ancortek SDR software. It's just using the export feature. So I took this and I just recorded myself walking down a room and then walking back. The room length is 25 meters, so it's awesome because the maximum unambiguous range of this radar in this mode is 25 meters. So this recording in particular had 128 samples per sweep. And so I set that as my file name. MATLAB will go ahead and parse that in. And what I do is I reshape that into the individual sweeps. So I have 100 right up here, FSK pulses. It's 128 samples per sweep, and then for 45 seconds I had a total of 45,779 sweeps that were taken. I then split that up into signal A and signal B. Signal A is just, it's going to be the first frequency that was transmitted, and signal B is the second half of that. That's going to be the second frequency. And then what I'm going to do is I'm going to set up 1,024 of these pulses in a, now I have a 2D, a two-dimensional matrix. One dimension is the sweeps, the second dimension is the number of sweeps, or the sweeps through time. And then I'll just go ahead and I'm going to keep a running measurement of the range that I have detected. And this is going to be the range of the maximum moving object in the field that it sees. So I'm just going to set it to all zeros based on the size of or the number of sweeps I have here. So I start my loop, and it's using a loop just because it's pretty simple to visualize. What I'll go ahead and do is I will go ahead and take, I'll make signal 1 and signal 2, and these are just the full sweeps, but they're limited to the FFT size that I want to process. So I'm processing 1,024 at a time. On the next iteration, it's going to process, or on the first iteration, it's going to process 1 to 1,024. On the next iteration, it's going to process 2 to 1,025, so on and so forth. It's going to keep incrementing by 1. I perform DC subtraction just by taking the mean of signal 1 and signal 2 and subtracting that out from signal 1 and signal 2. And this is the mean for the individual sweeps, not through time, but for the individual sweeps. I then run my FFTs. Oh no, you know what? I'm sorry. This is the mean through time, right here and right here. So then I run an FFT across time for signal 1 and signal 2. And then I make this signal 3. This is for the constant false alarm rate detection. And it's just mixing signal 1 and signal 2. They're multiplied together, and it's pretty good at cleaning it up, and I'll show you what I mean in a second. It'll go ahead and create figure 1, and then we're going to go ahead and write as an image the absolute value of signal 1, and it's absolute because it's complex signal. We're going to make an image of signal 2, and then we're going to make an image of signal 3. We're going to go ahead and then try to determine what is the maximum velocity bin from that FFT. So we're just going to take the max among all the sweeps, or I'm sorry, the maximum from the mean of all the sweeps. So if I look at, I have this already processed here. So this first one here is signal 1, the second one here is signal 2. This third one here is the mix of the two signals. And so what I want to do is I'm going to mean up and down, so I'm going to take the mean of these columns, and then I'm going to find the max out of all of that. I could also do a sum, that would probably work as well, but I'm just playing around for now. Once I determine that, it will give me an index. I plot the index here in this window where it says FFT bin of fastest moving object in field. It's going to be totally blue except for one column is going to be red, and that's going to be the index. And I then go ahead and take that index, and then from signal 1 and signal 2, I arbitrarily just choose some point in the sweep. It should be any point, but I'm seeing different results with different points. And that could just be with the radar settling after each sweep, changing frequency. But I'm getting good results at the 5th sample. I then take the index from the max up here, and then I determine the angle from signal 1, so that'll be phase 1. I then determine the angle of signal 2 the same way as before, that'll be phase 2. I then take the difference of those two angles, and then I perform modulo based on 2 pi, just because it can only, for the range equation, it should only be between 0 to 2 pi. So if it's any more, it's going to loop back around, which would result in an ambiguous range. So I then go ahead and calculate my range for this current interval. Again, this is a for loop, so it's going to be processing intervals. So my range for this current interval will be the speed of light times that phase difference divided by 4 pi times the frequency shift. And in this case, the frequency shift was 6 megahertz. I should probably just put that variable up there. I'll go ahead and plot that and label it. And so let's go ahead and we'll run this now. It takes a little while to load up the binary samples. And there it goes. So you can see it populate the range as it's running. And so what I'm doing is initially, during this first portion here, I am standing still a little bit away from the radar, down here. And then I start walking away from the radar. I keep walking, I keep walking, I keep walking until I get to the maximum. Well, really, it's the end of the wall, the end of the hallway, which was 25 meters. I stop. And so because I stop and I'm holding still for this duration of time between 1.5 and about 2.2, it is not going to detect me, and it's going to move to the next fastest object in the room, which I guess something was moving at like 12 meters. But then once I start walking back, it detects me again, and it'll follow me until I get back to the radar. And it looks like as I get back to the radar, in just about all these recordings, it seems to, how I had it set up in the room, there was just something moving at about 12 or 13 meters. And that had a stronger intensity than me walking back towards the radar. So let's go ahead and, I had 2 recordings I think that I can show. Load in this file. Oh, you know what? No, that was the wrong file. Sorry about that. Let me load in this first one here. If it'll let me. Yeah, this last one was a big recording. It was 45 seconds at 1024 samples per sweep, so it turned out to be, where is it? It's like a half gig of recording. This one right here. So the ones that I'm loading now are only about 68 megs. I think it's, oh, there it goes, great. Alright, so this is the second recording. Again, I just did the same thing. I started relatively close to the radar. It was a couple feet off. And I just started walking away from the radar. You can see it picks me up just fine. I get down to the end of the hallway, which is about 25 meters. I stop, so it again moves to the next fastest object in the field. But then once I start walking back, it picks me up, and you can see that range slowly decrease until I get within, again, it looks like there was just something moving at like 12 or 13 meters. I'm not really sure what that was, but there we go. So that's FSK range processing. And thanks for watching.